Now we are starting our next section in which we will discuss in detail all the user inputs that are required within the VOF model and various panels associated with the VOF model. In order to track the interface between different phases in VOF model, various schemes are used in order to solve the phase continuity equation. The phase continuity equation is solved, and using the solution of this phase continuity equation, the location of the interface is tracked. So VOF schemes basically decide how phase continuity equation is solved. As you can see in this panel, this is where we specify the volume fraction parameters and the VOF schemes within the multi-phase model panel. So there are two VOF schemes available, explicit and implicit. In case of explicit VOF scheme, phase continuity equation is solved uncoupled with the momentum and pressure equation. This is used only with unsteady simulation. Whereas in case of implicit scheme, the phase continuity equation, the momentum equation and pressure equation are solved together. So the difference between these schemes is basically how the phase continuity equation is solved within the sub-time steps. When it is solved together with the momentum and pressure equations, we term it as implicit scheme. When the phase continuity equation is solved uncoupled or separate from the momentum and pressure equation, it is termed as explicit scheme. Let us go into some detail of the implicit scheme. When we use the implicit scheme, the phase continuity equation is solved coupled with the momentum and pressure equation. Phase continuity equation is nothing but a continuity equation written for that specific phase. It has a general form in this way. This is the unsteady term, this is the mass flow rate term, that is conservation of mass flow, and this is the balance term. This is written for a particular cell or cell volume. Now, in case of implicit scheme, this is applied to a cell volume, and we can see here, this is the unsteady term, this is again the conservation of mass flow term, and this is the balancing term. You can see here that the time step order here is n plus 1. This is the current time step. So in case of implicit scheme, while calculating the continuity equation or solving the continuity equation, the velocity field that is taken from the momentum equation is of the latest time step. That is, it is solved along with the momentum equation. The momentum equation is also at n plus 1 time step, as well as the phase continuity equation is also at n plus 1 time step. So the momentum equation and the phase continuity equation are solved together. This is the term to watch for. N plus 1, that is the current time step. Let us see on the contrary what goes on within the explicit scheme. The explicit scheme solves the continuity equation in sub time step, but it is uncoupled with the momentum and pressure equations. That is, the phase continuity equation is not solved together with the momentum and pressure equations. Again, this is the general form of the phase continuity equation with the unsteady or transient term, the mass flow conservation term, and the balancing term. As you can see, this is the time step order, which is n, which means the momentum calculations or momentum flux is taken from a time step previous to the current time step. Current time step is n plus 1, whereas the momentum flux is taken from the previous time step. That is, the momentum equation is not solved along with the phase continuity equation. Note this n instead of n plus 1. So the phase continuity equation is solved uncoupled or separate from the momentum and pressure equation. This is the short description of the algorithm or short description of the process flow when explicit time stepping is used or explicit scheme is used. We start the current time step, we solve the momentum and pressure equation, obtain the solution of the momentum flux at given time step, and after that we solve the phase continuity equation. So the solution of the moment equation from previous time step is used within the phase continuity equation of the current time step. Whereas in explicit scheme, all these is solved together at the current time step. To turn on the explicit scheme, we go into multi-phase model panel, we click on VOF, and then within the volume fraction parameters, we select the scheme explicit. Let us have a brief comparison of the explicit and the implicit scheme. As shown here, this is where we can select either of the two schemes. Now we discuss the advantages and disadvantages of each schemes. When we say explicit scheme, what advantages come with explicit scheme is we can use the geo reconstruct scheme, which we will discuss in the further slides, Also, we get a clear and crisp interface because we already have the solution for the momentum equation from earlier time step. Also, we get highly accurate curvature calculations. Whereas the downside for the explicit scheme is that we get poor convergence for skewed meshes as well as poor convergence for the compressible flow. If we use the implicit scheme, we don't have any limitation on the Courant number. We will also discuss this in the coming slides. What do we mean by Courant number and its limitation? For implicit scheme, we can use larger time steps. Also, steady state calculations can be performed, and we can also obtain satisfactory convergence for poor quality mesh. The disadvantage of the implicit scheme is that there is numerical diffusion as well as inaccurate prediction of interface because we are solving phase continuity equation and moment equation together at the latest time step. So there may be some inaccurate prediction of interface. Now let us see how transient calculations are made when we are using the VOF model. In case we are solving a transient problem, as we all know, a equation is solved for volume fraction also, and a time step is required for that too. Now there is a choice to obtain the solution of volume fraction at each iteration or each time step. The user can decide whether volume fraction solution is to be obtained after each time step or after each iteration within that time step. We can also individually decide the time step for volume fraction. That is, the time step that is used for volume fraction equations can be different from the time step that is used for other equations like momentum or continuity. The default option or default setting is that volume fraction equation is solved after each time step. That is, after each time step of the continuous flow equation. If we wish to solve that volume fraction equation after every iteration, there is an option that we have to turn on. The option is called solve VOF every iteration. Remember that this option is to be used only when we see or we know that location of the interface will change as the other variables converge within a time step. Only then this option should be used, otherwise it is always recommended to use volume fraction equation after each time step. To activate this option, we have to type in console define models multi-phase volume fraction parameters and then turn on the VOF after every iteration option. Now let us see how Fluent decides the time step for VOF calculations. As we know already that the time step for VOF calculation is not the same as the time step used for other equations. So we have to take care or give a user input for the time step for VOF calculations. This user input that we give to decide the time step for VOF calculations is called the Courant number. Courant number is defined as a dimensionless number that compares the time step in the calculation to characteristic time of transit of fluid across a controlled volume. It is given by this ratio where delta t is the time step, delta x is the cell size, and v is the velocity of the fluid through that cell. So this comes out to be a dimensionless number. In the region near the fluid interface, Fluent internally divides the volume of each cell by the sum of the outgoing fluxes. Now if we compare this ratio, that is volume divided by flux, the result of this ratio is a time entity. So this time entity is actually the time it would take for the fluid to empty out that particular cell. So once this ratio is obtained, the smallest such time all the cells that the interface exists is used as the characteristic time of transit for the fluid element across a control volume. But this characteristic time is not used as a time step. We give a maximum allowed Courant number, and based on the above characteristic time and this Courant number, a time step is calculated. Let us see for an example if the maximum allowed Courant number that we give is 0.25, which is also the default. Now when characteristic time is calculated based on the above internal Fluent calculation, what is done is that this Courant number value, that is 0.25 or 1/4, this is used in order to calculate the time step. That is 1/4 of the characteristic transit time, 1/4 of the minimum value of the transit time that we calculated above is used as a time step. If we give 0.5, then half of the characteristic time or characteristic transit time will be used as a time step. So this is how the time step is calculated for VOF calculations. In order to specify the Courant number, we go to the multi-phase model panel, and within the volume fraction parameters, there is a option to specify Courant number. Courant number decides the number of sub-time steps, as we have discussed earlier. Default is 0.25, which is mostly robust. We can always change it as required. And depending upon this Courant number, the delta Tn is calculated, and that is how the calculations progress from a time Tn to time Tn plus 1. So this is a very important parameter when calculating unsteady multiphase calculations. Another option is the body force formulation, where we can tick or include the implicit body force. This particular option should be used when there are large body forces like gravity acting in our simulation, or if there are large density difference between the different phases that we are solving for. Also when there are strong body forces like rotational force, rotational acceleration, etc. In that case, we include this particular formulation, that is body force formulation. Now let us have a look at the process by which we define phases. We go into problem setup, then into phases, then either click primary or secondary phase and then edit. This is how the problem setup panel looks like. We go into phases, we click on primary phase or the secondary phase, whichever phase we want to define or edit, and then we click on this edit. Then this particular panel pops up. Right now we have clicked on primary phase. Here in this define phase panel, we can give the phase name and also enter the phase material. Currently it is air. So in this way we can define or edit any number of phases that we want. Similarly, we do it for secondary phase, where we click on secondary phase, then click edit, and then the secondary phase panel opens up. We define the name and define the material. Now if we click on this edit again in the phase panel, we can edit the material also. This is how the edit material panel looks like. So we can edit the material through the phase panel also. After we have seen how we define phases, let us see how we define the user inputs for phase interactions. Under the VOF model, any phase can be primary or secondary. Usually what we do is we select the phase that is predominantly present as the primary phase. That is, if air is present predominantly in a mixture of air and water, we select air as the continuous phase or the primary phase. Once we have defined the phases in our problem, these phases can interact with each other in various ways. Depending upon the physics involved, phases can interact either by having a chemical reaction, or mass transfer or mass exchange, and surface tension effects. These three are the most important in the VOF model. Now the question is, does Fluent model these phase interaction? The answer is yes, but in order for these phase interactions to be modeled, we have to give some user inputs that will define these phase interactions. For doing this, we go to problem setup, then to phases, then we click on interaction button, and then after the phase interaction panel pops up, we edit these user inputs. This is how it is done. Within the problem setup, we go on phases. List of phase appears. At the bottom of it, there is a button called interaction. We click on that. In this phase interaction panel, we see that we can define various phase interaction entities like drag, lift, collisions, slip, heat transfer, mass transfer, reactions, surface tension. We can also enable validation. As you can see here, a list of pair of phases will appear. If we have defined more than two phases, then we get more pairs of such phases. For each pair, we have to define an interaction coefficient or an interaction parameter. Let us now see in detail the phase interaction options. First, we will see chemical reactions modeling within the phase interaction options. For this, we need to turn on the species model, that is species transport model. For doing this, we go to problem setup, then to species. Then we go to species transport and turn it on. And then we edit all the parameters related to species transport. It is done in this way. We click here on models under the problem setup. The list of models appear. Then within species, we click on this species and this particular panel appears. Here we click on species transport so that species transport model is turned on. We select reactions, whether we want volumetric reactions or wall surface reactions or particle surface reactions, and other options that are related to chemical reactions and species transport. Now, after turning on the species model, we need to set up material properties for phases and their components. For this, we click on phase properties. Here, we can set properties for individual phases under the species model panel. So we select the phase, then click on set. Then the phase properties panel pops up. Here we select the phase name, then we select the material associated with that phase. Within the material, we can have different volumetric species or solid species or side species. We can change the component of that phase, the chemical component or the species component of that phase using the phase properties panel. So once this is done, our species transport and chemical properties of the phases and the composition of the phases is set. After this, we will see how to turn on the chemical reactions under the phase interaction panel. We go to problem setup, click on phases, then we click on interaction and then the reaction tab within the interaction panel. That is here, under the problem setup we click on phases, list of phases appears, then we click on interaction. Then the interaction panel will appear and within the interaction panel we click on this reaction tab to set our chemical reactions. All the user inputs that are related to chemical reactions for phase interaction are given in this reaction tab. We would like to say thank you for watching this particular lecture. If you have any doubts, please contact us on our email address. So thank you for viewing this particular lecture within the advanced course of multiphase flow. See you in the next lecture.